So there is a small announcement. So here's in the board we have given this T-shirt. Most of you received T-shirt. So there is a size, like by mistake we have given like some T-shirt with wrong size. So you just check your size, and in case you have got the wrong one, then you can change it. Okay, that's the thing. Yeah. Now I invite Professor Desue to chair this session.
Okay, so I would like first to compliment something I didn't say, that it was my pleasure to be here. And I think there is no real proof to give, except that I am not a masochist and I am coming that often, so it means that I have really pleasure in being here. So let us go now to real job. And it's my pleasure to invite Professor Adhikari to talk about some elementary algebraic methods in the study of zero-sum theorems. Thank you very much.
So, first of all, I'd like to thank the organizers for inviting me to this conference in honor of my good friends Srini and Kalyan, and to meet so many old friends and colleagues. So, I'm writing a book with Tangadurai, and this will be planning to finish this summer. So, recently I lectured on many topics around this theme, but of course I can give many disjoint talks on this. So while going through some zero-sum results, apart from some combinatorial arguments, we shall have a glimpse of elementary algebraic methods tackling these problems. So these methods here, they remind me this quotation of Rota. The mystery as well as the glory of mathematics lies not so much in the fact that abstract theories turn out to be useful in solving problems, but in fact that, wonder of wonders, a theory meant for one type of problems is often the only way of solving problems of entirely different kinds, problems for which the theory was not intended. Though in many problems in additive combinatorics this is perfectly fits in, but some results which I would see, there are alternate proofs, but maybe in some places these algebraic methods may be called the proof from the book, sort of. So some definitions, and so one observes that the following this sequence of n minus 1 zeros and n minus 1 ones, this doesn't have a subsequence of length n whose sum is 0 mod n. Now the 1961 result, this can be said to be the beginning of this branch of additive combinatorics, zero-sum additive combinatorics. So that says that this example is rather optimal in the sense that if you go one up, then any sequence of 2n minus 1 integers, they have a subsequence of n elements whose sum is 0 mod n. So this prototype of zero-sum theorems, has several proofs, and there is an article of Allen and Dubinir where there are about 7 proofs. Now, some among the most interesting proofs involve elementary algebraic techniques. So, following Allen, we give proof here using the Chevalier-Warning theorem. So, the statement of Chevalier-Warning theorem, if Fq is the finite field with q elements and Fi's are a set of finite polynomials, finitely many polynomials in n variables, such that the sum of the degrees is less than the number of variables, and if trivial solution is there, then there is a non-trivial solution. In fact, precisely the number of solution is a multiple of the characteristic that says from that it follows. So, now we do the proof of the EZZ theorem using this. Now one can see, it is not difficult to see that the most important part is the proving for the prime case. So once you put, so by induction on the number of prime factors of n, one can get the result from once you prove for prime. So we see the proof in the case where p is a prime. So we take a sequence here length 2p minus 1 over fp, and we consider this system of equations in 2p minus 1 variables and both of degree p minus 1, so that the sum of the degrees is strictly less than the number of variables, and trivial solution is there. So by Shivali warning, there is a non-trivial solution. So let I be the number of those indices where yi is not 0. Now since this is a non-trivial solution, capital I is non-empty. So from the first equation, it follows by Fermat's theorem, whenever it is non-zero, it is 1. So from the first thing, it follows that summing over I belonging to R capital I, this ai is 0. But in the second one, it picks up 1 in the non-trivial places. So number of non-zero entries is just multiple of p, but the only multiple of p between 1 and 2p minus 1 is p. So that shows that, sorry, can you go back? Yeah. So that shows that cardinality I equal to p. So this is a sort of magic proof. Now, by a simple inductive argument by the structure theorem of finite abelian groups, therefore one can deduce that any sequence of length 2n minus 1 elements of an abelian group of order n, it will have a zero-sum subsequence of length n. In fact, in this counter example, we can see when the group is z mod nz, then it is precisely 2n minus 1, the value, let us see. Was that on? Okay. So for a finite abelian group, the following definitions are suggested by the EZZ theorem. So capital EG is the smallest natural number such that any sequence of k elements in G has a zero-sum subsequence of length equal to cardinality of G. In fact, there is more general things we can consider. Requirement may be the length is multiple of the exponent, but here the cardinality of G if we take, then this is capital EG. Now EZZ theorem says that for an abelian group of order n, EG is less than equal to 2n minus 1. With the counter example we had seen earlier, that gives for z mod nz it is precisely 2n minus 1, and one knows that if it is not cyclic, then it goes strictly below, and it is n plus n by 2 if it is not cyclic but of the form, then this is realized by z mod 2z, the cyclic group of order 2, and another cyclic group of even order. Then if it is not in this form, then it further goes down to n plus n by 3 plus 1, and that is realized by groups of z mod 3z direct sum z mod 3mz, like that. So some results are known like that to some extent, and so then Sg is another constant which is suggested by the EZZ theorem. So this is, we require the minimal length which guarantees the zero-sum subsequence of length exponent G. So in z mod nz the exponent is also n. So we have E of Z mod Nz is S of that is equal to 2n minus 1. So the constant dg, we have to now another constant we have to bring. There are many constants, eta constant and Olson constant and all. They are important for various reasons, but here we will stick to those two and one more. So given any sequence of n integers, considering the sums a1, a1 plus a2 like that, this. So by pigeonhole principle, if none of them is 0 mod n, then two of them are equal mod n. So there is always a non-trivial, non-empty sequence, subsequence whose sum is 0 mod n. So one can ask this question in arbitrary finite abelian group, and in 1960s this question was asked, the smallest natural number such that a sequence of that length guarantees a non-empty subsequence, zero-sum subsequence. Now this problem was asked by Davenport in a conference in YO University in 1966, but much before that Rogers published an article 62, somehow it was not noticed by earlier researchers like Olson and others. So people, now we know it by Davenport constant. So I told all these things. So the problem of finding dg, this was of course had an application in mind, whereas this Erdos-Ginzburg-Zeev was a curious question, and this one was motivated by this, that if G is the class group of an algebraic number field and dg is the maximal number of prime ideals required in the decomposition of an irreducible integer, and there is sum which will require this many, and for everything you can fold them and bring less than equal to that. So this is important for various reasons in algebraic number theory. Now this also has application in graph theory, and also the well-known paper of Alford, Granville and Pomerance, that there are infinitely many of Carmichael numbers in 1994. They used a known bound for this Davenport constant. So the idea what is known about this, so I started at 10 or 15? 10. Okay. So clearly we know the same argument shows that dg is less than equal to n, and if we have G is the direct sum of Z cyclic groups of order n1, n2, and these, then writing this mg equal to this, so like 1 0 0 0 n1 minus 1 times, 0 1 0 0 n2 minus 1 times, etc., that gives the lower, this lower bound, and upper bound is again in this. So but I will go quickly because lack of time. So this, many people worked on that, more or less this is the now the best bound, whereas m is the exponent and 1 plus log this. This is the general known bound, this was used, and they gave another proof, Alford, Granville, Pomerance, in their paper. So the conjecture is that Gao and Geroldinger, that lower bound is true for rank 3 and for this type of groups, and this is established asymptotically. So fixing R and n goes to infinity. So I could have told bit more, but we have to hurry up because. So then there is another conjecture like this. So we are far from these things. Now for a finite abelian group of order n, this Gao established the following relation between this Eg and dg. Till then people are investigating these two constants separately. Now this was proved in 1996. So I will go quickly. So since for this easily it is this we have observed this easy observation by pigeonhole principle. From this theorem it follows that this EGZ theorem follows from this Gauss result. So then we started with some collaborators and some weighted. So we take a non-empty subset of these because this is meaningful because once you go above this, so the Davenport constant with weight A denoted by DAG is defined to be the least natural number such that any sequence there exists a non-empty weighted zero-sum subsequence, meaning there is a non-empty subsequence with some choosing, we can choose weights from capital A such that this becomes 0. Similarly, one defines this with the requirement that the length of the A-weighted zero-sum subsequence is of length mod G. Now, when you have capital A equal to singleton 1, that will correspond to the classical constants. So, let us go to G is equal to the cyclic group of order n. So, in our first paper where it was with Chain, Friedlander, Koniagin and Papalardi, we took this weight set and we found DAN is this by pigeonhole principle, and then this took some work to deduce that EA is n plus this log, as if this is n minus 1 plus this. So, this I will skip and go to some other. No, but there was. So, if we take the weight set to be the units in Z mod nz, if n is this, then take this sequence A1, P1, P1, P2, and then the product of 1 less than. So, then one can see that there is no A-weighted zero-sum subsequence, then that gives this bound. And since most often if we can choose a good counterexample, we are very near the truth. So, we conjectured that perhaps this is the truth and this is that. We take n minus 1 zeros and this sequence. So, then that suggests that this is greater than equal to this, but we thought that this should be the value, and this was proved by Luca next year and then later by Griffiths by another method. So, this result was proved. So, we have from this the DAN also follows. Now, let us see the group Z mod PZ. So, then one choice of weight is this, and this by combinatorial argument one proves that DAP is this and EAP is P minus 1 plus the integral part of P by R. Then when we take this A is the set of quadratic residues, then with Purushottam we proved this DAP is 3 and EAP is P plus 2. And with all these observations, calculations in the particular cases suggested that perhaps that Gauss result is true in the weighted scenario also. And when the cyclic case with Purushottam we had a proof applying Cauchy-Davenport. Here we will see a sketch, if time permits, a sketch of the proof with letter with Sauli and Purushottam using permanent lemma. So, how much time I have? 10 minutes? 10 minutes, okay. So, let us quickly go through a sketch of this proof. Now, permanent is like determinant with no sign. So, this is very important in combinatorics. There are many results about conjectures, which results and all. So, a special case of permanent lemma is this. This is a special case. I can refer to the general one by some articles of Allen. So, take a matrix over FP p minus 1 cross p minus 1, and suppose the permanent is non-zero. Then given any sequence of p minus 1 elements in this, there is elements in 0 1 p minus 1 such that this sum is when I equal to 1, then it is not equal to b1, I equal to 2 not equal to b2, like that. So for any non-empty weight set, this is greater than equal to this. So now A contains AB, because our with AB at least cardinality 2, so weight set. So A less than B, and this be any sequence of M elements where M is this. So we have to prove that such sequence has a zero sum with weight in our A. So first we assume that the number of non-zero elements in the above sequence is at least p minus 1. So without loss of generality, by interchanging, we assume the first p minus 1 are non-zero. Now consider the matrix where this is equal to b minus SCJ for this. Now this element we choose, and all other elements are denoted by, give them names this, b1, b2, bp minus 1, just give them names apart from this element. Now we can choose, because see easily that permanent is non-zero. Now there are this by that theorem. Now our matrix, all the rows are same. So the same thing, for every I we get same thing. So this is not equal to this for this is for any of those. Let us go. So this is not equal to any of these b1, b2, b this. So it has to be equal to this. So that forces that this sum. Where are we? Yes. So this sum has to be equal to that remaining element, because this is not equal to any of the other elements, and then we rearrange. Now if epsilon is 0, then you get ACJ. If it is 1, then this gets cancelled, you get BCJ. And last one is this. So you get a P length zero sum subsequence with weight set AB. So that gives that. Other side is simple combinatorial argument would give this. So this proves that in the prime case, Z mod Pz cyclic group of order, prime order, we have proved that conjecture, that Gauss result in the weighted scenario. Then this is another result, bit more general for arbitrary abelian groups, but again here the cardinality of A, so we are not recovering Gauss result from any of these results. So cardinality A is greater than or equal to 2, and the condition is this GCD condition. Then we have again this result holds. So that works for many. If we have in the weight set 2 elements consecutive, then that works. So and from this, even that prime case trivially follows. So this, after this, then 2009, Wan and Zheng proved for general cyclic group, and Zinkiewicz, Marcha and Ordaz, they proved for general abelian, finite abelian group. Now the thing is that both of them uses this is a generalization of Kneser's addition theorem by DeVos, Godin and Mohr, which came in 2009, and both of them use this. So there is no other proof. So this could not be proved before that. Not that if we had this we could have proved. So Yuan and Zheng first noticed that this is very much applicable, and then they also used this and they could. That is, proof is difficult. Okay. Then though we started our investigation as a rather curious thing to see whether get some idea about the conjectured bounds in the non-weighted case. But then later there are many people have found applications in algebraic number theory and coding theory, and this is one of the results which I had quoted, but maybe I will go a bit ahead. So I can give references of, one can look into this in Google. And so many people now, there is another thing, because of these applications, there people are trying to find good bounds for these constants. So we are not going through those now. Then there is another constant SG. There are many results we had done, and there were these two variables, this conjecture remained open, and Ryer proved in commutative way. But this Ronier's method was very useful. This is a linear algebraic method. And 2-3 minutes. Yeah. So I'll quickly go this. There was a Ronnier idea was to construct a polynomial in many variables which vanishes at all points other than that 0, 0, 0, 0. And there, so one gets at vector 0, you have 2, and this is 0, all non-zero points. Then trivially you construct this, which is also does that, but degree is different, but then that contradicts about that, because these monomials, these constitute a basis. So I am just giving a just rough idea about what is this, because I want to tell about this method little bit. So there are some references I have given. If anybody wants, I can give the slides. So we started in the weighted generalization. So I will mention where that this is a very good result we could get, but this was a commutative method. So here the asymptotic behavior of this for a finite abelian group of even exponent. So then we get a very asymptotic result. For the odd things, we tried with several students earlier, and now we get this result in 2022, and if P is an odd prime and D is less than equal to 4, and you have this rank 4 abelian P group, and Q is equal to QD, the exponent, then for any integer k greater than 2, that if you have this, you require a zero sum of length kq, then it is exactly equal. Whereas Ronier's method in the classical case was just, little less than, the exact conjecture. But here we could get exact values, but again with lower rank only. And when D is less than equal to 2, then we can even get SQA. So we can get the analog of that classical constant here and get the exact value. And as is clear that once you do for A equal to 1, 2, you can do for any scalar multiple of the weight. So with this we stop. Thank you.
Okay, thank you very much, Sukumar. Are there questions, comments, remarks, proofs? Everything was perfectly clear. Thank you very much. Green one. Yeah, I understand. So, on behalf of the organizers, I have the pleasure to offer you what? Next talk in, 5 minutes about. start with a few minutes. Okay, it's really my pleasure to introduce Shankar Narayana. And the first time we met was during indeed my first visit to India. It was in '87. And Shankar was a kid at that time. And I was very happy that he took time to introduce me to Mumbai and all the mysteries of Mumbai. And so now let us back to real business. And so please, Shankar, we are going to talk about on the distribution of the restricted sequence of integers 2 to the little omega of n. Thank you very much. Please.
Okay, thank you very much for the kind invitation and my best wishes to the birthday babies, Srini and Kalyan. Yeah. So, today what I am going to talk about is, this is a work jointly done with my student, Mr. Venkata Subbareddy. This has already appeared recently actually, 9th December it has come out, the paper has come out. So, okay, some motivation, maybe motivation I can skip because all are specialists. So, well, maybe if you define the Mobius function mu1 to be 1 when n is equal to 1, minus 1 power k when n is product of distinct k prime factors, 0 otherwise, then of course one knows that the bound of this command in absolute value less than or equal to some constant times x power half plus epsilon, this is equivalent to Riemann hypothesis. One knows that. So, generally when you have a good arithmetic function and when you are interested to study about the summand with the weight Gn, then because left hand side is a discontinuous function, all that you can expect is either an upper bound or an asymptotic formula depending on the situation. So, naturally one has more leverage if you know the generating function attached to the coefficient Gn, namely the L function Lg to be summation n is equal to 1 to infinity Gn over n power s. And if you know more analytic properties, very nice properties, then of course you can expect more information about this summand. So, one of the important problems in number theory is the divisor problem, namely the summation n less than or equal to x dn, the problem considered by Dirichlet, which has such a main term and error term of course. The error term probably the best result as of today known is something like Ex less than x power 131 divided by 416 plus epsilon due to actually, and one knows that such omega result holds good for this error term, and I think this result has been improved by Hafner to this. So, you can see that there is a long gap here for various arithmetic functions people are interested. So, in this lecture I just want to mention that if you consider the function 2 power omega n, where omega n is the number of distinct prime factors of n, of course you know that this function 2 power omega n is multiplicative, and in the literature of course one knows that summation n less than or equal to x 2 power omega n has is satisfying certain asymptotic formula with the main term, and the error term is somewhat like O of x power 1 over 2 plus epsilon. I am not x power epsilon, I am not saying very clearly, I mean you have more refined estimates in the literature. What we are interested in this work is that instead of the summand runs over all the integers, if you restrict to our sparse sequence of integers, what will happen? So, our aim here is to see the following, namely we define the function f1 as f1 is equal to 1 and f1 to be 2 power omega n if n is powerful, 0 otherwise. So, so that you can easily see f1 is multiplicative here, and if you see the L function attached to this arithmetic function is nothing but this guy, and because it is multiplicative by Euler product representation, one has such an Euler product, which is absolutely convergent in the half plane real part of s is bigger than 1 over 2. And of course, naturally you expect Riemann zeta function and other factors come into the picture here, and of course, here life is somewhat rather difficult, more difficult than usual 2 power omega n. 2 power omega n case, if you take that L function attached to those coefficients is nothing but zeta square s divided by zeta 2 s or something. But here you need little more information, that is what we do here. In the case of Riemann zeta function, of course, you have a functional equation of this kind, and this chi s, the conversion factor which behaves in absolute value as mod t power 1 over 2 minus sigma in any fixed vertical strip for large T. So, let me just recall the Riemann hypothesis, which tells you that all the non-trivial zeros of the Riemann zeta function, they lie on the critical line, real part of s equal to 1 over 2, and we call the strong Riemann hypothesis. The stronger version is that all the non-trivial zeros of the Riemann zeta function lie on the critical line, and each such zero is simple. As of today, whatever the computation results known for a larger height, they support the strong Riemann hypothesis. This is just not a proof, this is just an evidence, that is all. Okay. So, one knows some zero-free region for the Riemann zeta function due to Vinogradov. Later works, of course, some kind of improvement on the constants and some had been done. So, what we show here is that in the sparse case, that means that we are considering this summand, summation n less than or x, f1, in the case f1 which is defined f1 is equal to 1, f1 is equal to 2 power omega n when n is square full, 0 otherwise. For this summand, we show that this has such a main term, and error term is going to be something like x power 1/4 and some small increasing function. This is what we prove. Of course, this result is unconditional, and I should also mention that from the generating function, when you investigate, it is not too difficult to find out. Of course, there are some certain standard methods which one can refer to, a paper of Balasubramanian and Ramachandra, I think which appeared in 1980s in JNT, I believe, from which one knows that this error term, for example, one can show it is something like omega x power 1 over 8, I believe. Yeah. So, still there is a long gap. So, the second question is there a way here to improve this? So, to improve this, of course, life becomes very difficult. So, what we do is that we assume strong Riemann hypothesis. Okay, you assume strong Riemann hypothesis. Can you say something much better? Indeed, I can say something more. That is what the second theorem tells you. Second theorem, in fact, when you assume strong Riemann hypothesis, namely all the non-trivial zeros of zeta ls for L is equal to 2, 3, 14. Of course, for all these Riemann zeta function, if I assume the strong Riemann hypothesis, then of course I can show that this sum has some extra main terms. One more main term is there. Yes. And then I can show that the error is something like O of x power 5 over 22 plus epsilon. One can see 5 over 22 is strictly less than 1/4. So, that improves, of course, with you have taken out some main terms involving the zeros of the Riemann zeta function effectively. Yeah, so the proof, let me just sketch the proof. Just before, let me say what happened. Yeah, so some lemmas. So, I have such an Euler product representation in the half plane real part of S bigger than 1 over 2. So, let me just recall, whenever you have Fn is 0, whenever p square does not divide n, etc. So, you decompose this L function to the following. This lemma 1 is somewhat crucial. Let me tell you, I think I need a clear picture at least up to this level, namely real part of S is bigger than 1 over 15. So, until then I have to do, then only I can prove theorem 2, at least by this argument of this article. Okay. So, how does one achieve this continuation? So, what we do is write x is equal to p power minus s in the Euler product, and of course, you as long as real part of s is bigger than 1 over 2, you observe mod x less than 1. So, to prove this particular expression, you first observe 1 plus 2x square plus 2x cube, etc., into product of polynomials in the form 1 minus x power m or its inverses from m is equal to 2 to 14, possibly with some error terms. This is what we do. Of course, for a fewer product terms with mind manipulation one can do. When you want longer thing, of course, we use Mathematica to confirm everything. Okay. So, you have such a representation. So, you can observe that this infinite sum is a product of these two, then you adjust one by one, etc., with an error of x power 15. That is what is happening. So, that of course, I do not go into. So, finally, you put x is equal to p power minus s, which will lead to your f of s is nothing but this quotient of these zeta functions times h1s, where h1s converges absolutely and uniformly in the half plane real part of s is bigger than 1 over 15. This is what I want for proving theorem 2. So, the next lemma is of course the shrinked version of lemma 1, which is first few factors I have taken, and H2S I am just writing this way. So, one observes that in the half plane real part of S bigger than 1 over 15, the function f of s has singularities, namely poles at the points 1 over 2, 1 over 3, 1 over 7, 1 over 8, 1 over 12, 1 over 13, 1 over 14, as well as at the non-trivial zeros of zeta 4s, zeta 5s, zeta 6s, which appear in the denominator of that product. Of course, one knows that because I am assuming strong Riemann hypothesis, namely the zeros of the Riemann zeta function lie on the critical line, as well as they are simple for various L is equal to 2 to 14. So, I can explicitly compute the residues at s equal to 1 over 2, 1 over 3, 1 over 7, 1 over 8, 1 over 12, and at these points 1 over 8 plus I gamma 1 over 8, 1 over 10 plus I gamma 1 over 10, 1 over 12 plus I gamma 1 over 12. All these of course with certain orders are there. So, you just compute the residues, then apply Cauchy residue theorem, find out the estimates for the left vertical line contribution and horizontal line contribution. Of course, you need to use certain mean value estimates, maybe functional equation and so on, and try to see how much one can tighten the belt here. So, so some details are given. And next lemma what I use is a fourth moment of the Riemann zeta function, which is well known to everybody, and this is of course a result of Bidov, and then another result, an important result which tells you the Riemann hypothesis, which implies that for every sigma between half and 1 for large t, the Riemann zeta function as well as 1 over of course here sigma is strictly bigger than half for this. It should be O of mod t power epsilon if you assume Riemann hypothesis. So, I will use all this along with functional equation also. So, once you have all this, I start with the Perron's formula. So, this is the sum. The line you start with the 1 over 2 plus 1 over log x, and you have such an error estimated from the tail portion. Then you move the line of integration to 1 over 4 minus the constant over log t power 2/3 double log t power 1/3. I just for simplicity write gt to be the junk. Then you apply the Cauchy's residue theorem, and one notices that for the first theorem unconditioned result I use lemma 2. F of s has two poles, one at s equal to 1 over 2 of order 2, another at s equal to 1 over 3 of order 2. That gives you essentially the main terms of this type. Then these are the errors coming from the horizontal and vertical line contributions. This is the tail portion. So, if you estimate the left vertical line contribution in absolute value, precisely maybe you use functional equation and so on, and then you just you observe that the contribution is nothing but x power 1/4 minus c by gt, some extra factor, small factor. Yeah. And the horizontal line portions I2 and I3 in total, they contribute this much. Then here of course I have to use the functional equation, and then you estimate explicitly what happens here. So, what I see here is that as long as my t is bigger than x power 1/4, this is the estimate comes into the picture. These two are the dominant error terms. Now you have to choose t. We choose t such a way that these two are of similar order. That tells you exactly this is the error term what we climb. This is unconditional. Of course, the second theorem is somewhat more interesting, though it is conditional. It gives some light. Of course, lemma 1, that's what I told. That has some crucial computation effectively. So, in this case, first of all you start with the line of integration here 1 over 2 plus 1 over log x, the tail portion error you have. This itself tells you that error time improvement is possible only when t is bigger than x power c star, with c star is strictly 1/4, bigger than 1/4. That tells clearly. So, provided by some means if you can extract a few more main terms somehow. That is what we do by assuming the strong Riemann hypothesis. So, you move the line of integration to real part of s is 1 over 14 plus 1 over double log x, and then you see poles from s equal to 1 over 2 of order 2, 1 over 3 of order 2, 1 over 7 of order 2, 1 over 8 of order 4, 1 over 12 of order 5, and so on. And simple pole, because of your assumption strong Riemann hypothesis, a simple pole at each s is equal to 1 over 8 plus I gamma 1 over 8, a pole of order 2 at each s at 1 over 10 I gamma 1 over 10, a pole of order 3 at each s 1 over 12 plus I gamma 1 over 12. They come from these factors which appear at the denominator. Yeah, with modulus gamma 1 over 2, modulus gamma 1 over 10, modulus gamma 1 over 12 is strictly less than t, up to height t you have to count. So, when you do all this, anyway residues you have computed, you just fit in all these things. So, precisely you have J1, J2, J3, this residue and this error. So, the left vertical line contribution again you do it on this line 1 over 14 plus 1 over double log x, use the functional equation and fourth power mean of the whatever, So it tells you that the estimate is going to be something like x power 1 over 14 plus 1 over double log x t power 4 by 7 plus 22 by double log x plus some 52 epsilon or whatever. Epsilon is any small positive constant. And the horizontal line contribution, of course, just to see more clearly, what we do is we split this interval into a few parts like 1 over 14 to 1 over 12, 1 over 12 to 1 over 9, etc., etc. Then you can see more clearly, and you can use wherever necessary functional equation of the Riemann zeta function, conversion factor, growth, you have to take it into account. All this, if you do, it tells you that all these things are controlled in absolute value by these expressions. Of course, you know that in any of these maximums, you can see that these functions as a function of sigma, this is monotonic in that interval. So maxima appears on the extremities. So take the left bound and right bound for each interval, and totally that will tell you these are the estimates what you get. Precisely this estimate is going to dominate over all other things as long as t is bigger than x power 1/4. Once you observe that fact, you can see that the residues coming from these guys, they are all going to be small in any case. So these three main terms will be there, and then these two terms are going to be there. Yeah. Now my job is to choose t. I choose t such that these two are of same order. So what we do is here, t is something like x power 3 by 11, which is strictly bigger than x power 1/4. That does your job, and that gives you precisely what you want, with of course these three extra main terms, with the error is of x power 5 over 12 plus epsilon, 5 over 22 plus epsilon, which is much better. Of course, you have three summed main terms, whatever. But the whole point here is that one observes here, for instance, the S1 sum. If you take this is the sum, my t is something like x power 3 by 11. That is my choice. So trivially, if you take the absolute value inside and so on, this is going to be some maximum of these constants, and x power 35 by 88. That is much worse. Similarly, trivial bounds are much worse. On the other hand, what one observes here is that because of the oscillatory factor x power I gamma business, you expect enough cancellations to happen, but we are not in a position to prove anything on the enough cancellation. Thus, we are tempted to make the conjecture that these three summands S1, S2, S3 are of order of x power 5 over 22 plus epsilon on the safe side, though we are not in a position to prove anything on this point. I think I am through. Yeah.
Good. Thank you very much. Well, are there questions? Yes, please.
Yeah.
So I have two questions, if I may ask.
Please.
So this x to the power 1/4, the length of the interval. I mean, how are you getting x to the power 1/4? Is it
Which
possible to push below?
Which one?
So if you, in your proof, this t length you are taking as x to the power 1/4, right? T is greater than x to the power 1/4. I think in both the theorem you are using that.
No. Just to see.
Yeah, so
Just to see, these are all smaller. If you put t is at least x power 1/4, these are all smaller, so I can omit.
yeah, so what I'm saying is it possible to have do you expect to have a more finer estimate so that for smaller length also?
Okay, let me tell you. Yes, I can understand what you want to say. See, the thing is, maybe you can continue in a better region, you can have more factors. It may improve little bit more, but with more main terms you should be able to take out. That is also there. But even the improvement will be at third or fourth decimal. This is what I expect. But more main terms will come into the picture. Only under the assumption of strong Riemann hypothesis still, yes? Yes. Unconditionally we don't claim anything here. Yeah, under SRH.
I have another question.
Yes, please.
Could you please go back to theorem 2 statement?
Theorem
2.
2.
Yes, so next question.
Statement. Yes. Yes.
So is it possible to say something about the, the constant of the lower order term, like C3, C4, particularly sign?
They, I don't have any idea. These are some real constants C1, C2, C3, C4. But D1 gamma, D2 gamma may be complex constant. Yes?
Okay, thank you, sir.
Yeah.
Nice talk. Thank
Yeah.
you for the nice talk.
Thanks.
Is there any special form for this error term, like Voronoi or some kind of exponential sum to work with?
Maybe, we don't know. It should work out. Yes, I don't know. Maybe.
But is it expected to have such a thing?
Maybe. Because usually, you see, of course, here sparse sequence you are doing it. Usually, if you take 2 power omega n for all n, it behaves like a divisor function. I mean, it agrees with the divisor function when n is a prime. Yes. That much only you can say, nothing more. Yes. Yeah.
Yeah,
Yeah,
I have a
please.
question. So, is there anything better that you can do if you consider smoothened sums? Like you add a compactly supported function and you take summation f of n, let's say phi of n by x, and then
You should try.
then you will get a better handle on the other terms, and maybe I don't know.
You can try.
Okay, and just since we're on this slide of theorem 2, the exponent of x, right? It's like x to the 1/12 is the smallest main term that you have. I think it's on the next page.
Yes, yeah.
But your error term is like x to the 5/22.
Hello,
So,
boss. That is why I told you x power I gamma is there.
okay.
That is the oscillatory terms. So there may be cancellation. We don't know.
So you expect this, whatever the sums to be, also be go 5
Small.
over 22. To
We
be
expect
okay.
to be small.
Okay, but,
But-
you have this precise version.
But we don't know how to prove.
Okay, okay. Thank you.
Okay. I would like to raise a question. So you start with the divisor function,
Yes.
and then you mention the function which is in some way the strong multiplicative function associated to the divisor function, which is 2 to the omega of n,
Yes.
which doesn't depend on the prime powers.
Yes.
But you are summing them over square full number and not over all the numbers.
It's
Why?
sparse sequence. When you restrict the summand, what is the behavior?
Yeah, but what about the divisor function then over this set?
Very difficult.
Okay. Yeah. Okay, some other question or remark or? Okay, if not, then, yeah, sure.
So you mentioned the divisor function. I had the same query. Have you thought of that problem instead of 2 to the power of omega n?
Yes.
You have just omega n, and what happens?
Just omega.
Yes.
Sir, Ramanujan has done so much of work.
Yes.
Yes.
So, can you just give a reference for that?
I think it is available in the literature. One can check it.
Not much that you are interested in.
No, I haven't done much, but there are references.
And it is also true that square root of Riemann zeta enters into that
See,
Dirichlet
I
series.
think, see, omega n minus some double log n mod square, and if you take, it has some about, roughly it behaves like double log n or something like that.
Thank you.
Yes.
Okay, so if no more questions, then we may enjoy a little break and come back at 12:30 as in the
Okay,
program.
thank you very much.
Thank you.
Oh, come. Come.
Okay, on behalf of the organizers,
Come here.
it's
Let
just
us
my
have good
pleasure
photograph.
to give you this. I was keeping for 40 years.
Thanks a lot.
Okay, great.
Thank you very much.
Take it back. So, okay, next and last speaker in this morning session is Kaninika Sinha, and she'll talk about explicit zero-free regions for modular RL functions. So please, Kaninika.
Thank you very much. Many thanks to the organizers for such a beautiful conference and for the opportunity to speak at the birthday conference of Srini and Kalyan. They've both been very friendly and kind to me since my student days, and I'm honored to speak here, and I wish them great health, happiness, and lots of mathematics. So today I'm going to talk about explicit zero-free regions for modular L functions. So let's set up the object of our interest. So we are going to focus on non-CM Hecke-Nu forms of a given weight k with respect to gamma naught of n. Here k and n are positive integers with n square free and k even. I'll tell you later why it helps to have square free n for the kind of explicit results that we are after. So such a Hecke-Nu form has a Fourier expansion where lambda sub f of n denotes the normalized Fourier coefficient, and these are also the Hecke eigenvalues corresponding to this Hecke eigenform, and lambda sub f of 1 is equal to 1. By the Ramanujan-Deligne bound, we know that lambda sub f of p lies in the interval minus 2 to 2 for all primes p. And the object of our interest is the L function, LSF, corresponding to this Hecke-Nu form defined by the Dirichlet series given by the lambda sub f of n. So this is absolutely convergent in the region real part of S greater than 1. Now we also know, because of the multiplicativity relationships among the eigenvalues, this has a nice Euler product representation. And some other properties that we know from the basic theory of modular forms is that LSF can be analytically continued to an entire function on the complex plane, and it is non-zero when real part of S is greater than 1. So we are interested in zero-free regions of LSF in the vertical strip when real part of S lies between 0 and 1. And we'd like to find out how to use information about the function in the region real part of S greater than 1 to derive zero-free regions to the left of this. Now zero-free regions for LSF and their corresponding symmetric power L functions Ls sim to the m of f yield effective estimates for partial sums, for sums as you run over all the primes up to x of the Hecke eigenvalues lambda sub f of p to the n. And this is in the spirit of the prime number theorem, the sums of the von Mangold function. And the main goal is to understand how to use zero-free regions. I mean, not the main goal of this talk, but an important application of the study of zero-free regions is to derive estimates for sums of this form. And we saw other types of L functions and other types of sums of arithmetic functions in Professor Sankara Narayanan's talk. So now we'll be focusing on these types of sums. So in particular, a very nice application is to error terms that arise in what is called the Sato-Tate distribution theorem. So what is the Sato-Tate distribution theorem? It is the assertion that your sequence of eigenvalues lambda sub f of p as you run over all the primes converges, it is equidistributed with respect to what is called the semicircle or the Sato-Tate distribution measure. And if you wanted to prove an assertion of this kind, you have to prove an asymptotic relationship between sums of h of lambda sub f of p, where h is any continuous function on minus 2 to 2. And you don't really have to actually do it for every continuous function. It is sufficient to prove this asymptotic for a family of polynomials encompassing polynomials of all degrees. And in particular, if we were to take the family of Chebyshev polynomials of the second kind, for example, because of the relationship between the lambda sub f of p and lambda sub f of p to the higher powers, this Sato-Tate theorem is actually, the Sato-Tate asymptotic is equivalent to the following assertion in terms of the sums of the coefficients that we are interested in. So for m is equal to 0, there is nothing to do. This is just 1. But for m greater than 0, so any positive m, we want to show that this limit is indeed 0. And a weighted version of the same asymptotic is to show that for any m greater than or equal to 1, the sum of lambda sub f of p to the m times log p is little o of x as x goes to infinity. So analogous to the fundamental ideas in the proof of the prime number theorem, wider zero-free regions for these symmetric power L functions lead to sharper estimates for these sums. So not only do we get effective estimates, not just little o estimates, but big O estimates, but one can also derive effective absolute constants in these estimates with the help of zero-free regions. But the main thing is, wider the zero-free regions, better would be your estimates. These estimates further lead to effective error terms in the error term between in the Sato-Tate distribution law. Okay, so let's move to what we know about the zero-free regions for these L functions. So in 1940, Rankine showed that this function, so far by classical theory we know that this function is non-vanishing when real part of S is greater than 1, and Rankine showed that it does not vanish on the line real part of S equal to 1, and this leads to the estimate sum of lambda sub f of p times log p is little o of x. So the estimates that we were mentioning for m equal to 1, Rankine was able to show this, and this settled a conjecture of Hardy on the Ramanujan tau function, which he had made in the 1920s. In 1972, Moreno refined the techniques of Rankine along the lines of the prime number theorem and established a zero-free region. So this is the first, whatever the classical zero-free region one derives for modular L functions, LSF. So these are regions of the form real part of S is greater than or equal to 1 minus b over log of absolute of t plus 2, where t denotes the imaginary part of S. And it is important to note here that we do not have a precise value for b. All we know, the classical form of these results is that there exists an absolute positive constant b such that a zero-free region of the following form holds. Using this zero-free region, Moreno derived the following estimate. So he's making the previous theorem more effective. And so I forgot to mention, Moreno's theorem was specifically for k equal to 2, but the ideas can be generalized to higher weights as well. So with respect to higher weights and levels, we know that there exists again an absolute constant b such that LSF does not have any zeros in regions of this form, and we see the dependence of this region on the important parameters in this case, namely the level n and the weight k. And from this it follows that this sum that we are trying to estimate as an application of zero-free regions is of the following form. So, and there should be a k as well, square root of n times k. Okay. Now the widest zero-free regions are of course predicted by the Riemann hypothesis, and one wonders what would happen to this estimate if we were to apply the Riemann hypothesis. So in this direction, in 1985, Kumar-Murthy showed that for a new form of weight 2, which is associated with the non-CM elliptic curve E over Q. So basically he's restricting his attention to non-CM new forms with integer coefficients. If all the symmetric power L functions are automorphic, I'll tell you more about it later. At the time when Kumar-Murthy proved his theorem, this fact was not known. So assuming that all symmetric power L functions are automorphic and satisfy the GRH, then for each m greater than or equal to 1, we have the following O estimate, and notice, so now you have x to the half, which is essentially the best possible estimate, best possible exponent you can get, and this comes by assuming the GRH. Okay. In 2017, Rouse and Thorner generalized this, okay, I might fall down. Rouse and Thorner generalized this to a non-CM new form F of square free level n and weight k, again under the assumption of automorphy and GRH, and they obtain this O estimate, where here again you can see clearly the dependence on the level n and the weight k. Now in 2020, Thorner proves an unconditional version of this theorem. So he shows, so between 2017 and 2020, the first assumption that we had made, namely that of symmetric power L functions being automorphic for all m greater than or equal to 1, was proved by the work of Newton and Thorne, and using that, Thorner is able to derive a zero-free region for the symmetric power L functions in terms of, so the expression looks very similar to the zero-free regions that we mentioned before, but now this very nice quantity, namely the analytic conductor of your L function, comes into the picture, and this analytic conductor, as we know, captures a lot of important information related to this, this symmetric power L function. But again, we know that there exists an absolute constant for which this happens, but we don't have so far a value for this constant C. And an explicit constant was obtained for the first time in 2022 by the work of Hoey, Iskander, Jin and Suarez. So just to mention, Thorner does not require square free level n, but when you need to make your constants explicit, it helps a lot to take square free positive integers. So under this condition, let us take beta plus it to be a 0 of our L function, such that beta is greater than half. Because of the functional equation, it's okay to just consider beta greater than half. It will also give you information of what happens when beta is less than half. So in this condition, beta is less than or equal to, if beta plus it is a 0 of LSF, then beta is less than or equal to 1 minus this expression here, where you have logarithmic of a function involving n and k and the imaginary part of your 0. But it is important to note here that for the first time, we actually had an explicit constant here, which is approximately 445.7. So in the summer of 2023, I was attending a program on explicit number theory in Vancouver. So some of us got together and we started thinking about zero-free regions, and we were wondering whether we can improve the constants in the previous theorem. So the work I'm presenting is joint with Stephen Creech, Alia Hamieh, Simran Kunga, Jacob Streipel, and Kinmin Kelvin Tsang. So we were able to significantly improve the constant in our zero-free region from 445.7 to approximately 16.71. So there are no, so this, if beta plus it is a 0 of LSF and absolute of t is greater than or equal to 1, then we obtain a bound for beta of this form. Now this bound is obtained by a very elementary and interesting technique that was introduced by Stechkin in the year 1970, but had for some reason not been explored in the context of modular L functions. So I'll just give you now a brief curated history of zero-free regions, starting with the zeta function, and I'll also present essential parts of Stechkin's technique to you in the context of the Riemann zeta function, because it is easiest to understand in that context, and then in the last epsilon many seconds, I'll tell you how you can adapt it to modular L functions. So those of you who've seen theorems related to zero-free regions would be very familiar with this trigonometric inequality. It is the ancestor of all zero-free region arguments. So we've got this trigonometric polynomial, And we apply this to the following, the negative of the logarithmic derivative of the Riemann zeta function. So you have minus zeta prime by zeta, which by other considerations using the Dirichlet L functions and its Euler product, you can write it in this term, in this, as this sum, where lambda of n is your von Mangold function. So you can now adapt your trigonometric polynomial and fit, so you now take this combination of your zeta prime by zeta in terms of this trigonometric polynomial, and derive that the real part of this particular combination involving sigma, sigma plus it and sigma plus 2it, this turns out to be this sum where all the terms are non-negative. So the real part of this expression here is non-negative, right, when real part of s is greater than 1. Now we have, if we apply the Hadamard factorization theorem for the completed zeta function, we can adapt it to derive that the real part of minus zeta prime by zeta is this expression, which involves some nice functions such as the logarithmic derivative of the gamma function, and the most important part is this particular sum coming from all the non-trivial zeros of the Riemann zeta function. Okay? Okay. Now, what we observe is that since the real part of s is greater than 1 and the real part of this row lies between 0 and 1, with some very elementary calculations, you can show that each term in this sum is in fact non-negative. Okay? And so what we do is we just choose one particular 0 of our choice from this, let's call it beta plus it 0, and we bound the real part of minus zeta prime over zeta by this whole thing here, the real part of, this whole thing here, minus just the real part of 1 over s minus this particular 0 row. Okay. Okay, then we apply well-known bounds on the gamma function, in fact which come from the Hadamard factorization of 1 over gamma of s. We apply those and we end up getting a bound of this form, but again this does not give us precise constants, but it tells us that, at least the classical argument tells us that for a positive constant a and for absolute of t greater than or equal to 2, the real part of minus zeta prime over zeta is bounded above by a times log t, a log of absolute of t, minus 1 over sigma minus beta. We put this bound, and for the case when t is equal to 0 also we have a bound which can also be derived from the above information, and we put all of this in the expression coming from the 341 polynomial, which we know to be non-negative, but now because of the bounds that we have, this bound and this bound, we can put it into the upper bound for this 341 polynomial, and then by some shifting around we end up getting this inequality. 4 over sigma minus beta is bounded above by 3 over sigma minus 1 plus a constant times log of t. And by making, now this is true for any sigma greater than 1. So by making an appropriate choice of sigma, we deduce, so this particular choice, 1 plus 1 over delta log absolute of t, where delta is anything which is greater than capital B. So in particular for b plus 1, you can take this. We end up getting a positive, we deduce that there exists a positive constant c such that beta, the real part of the 0 that we have isolated, is bounded above by this particular quantity. But again, we don't know a precise value of c, and one wonders if you can go back to the classical argument, make it effective at every stage and establish an explicit constant c. So this is the beginning of the field called explicit number theory. So now we go to this very nice technique of Stechkin in the 1970. So he observes the following. So let phi to be this particular constant, which is something greater than 1, and let us take sigma to be something which is greater than 1 but smaller than phi, and let us take sigma 1 to be something that is slightly to the right of sigma, and in fact this is the precise formula for sigma sub 1. Now we take two complex numbers s and s1 which have the same imaginary part, but the real part of s is sigma and the real part of s1 is sigma 1. One now defines, I'll tell you in a minute why this is helpful. So Stechkin defines this function here, f of s comma z, which is the real part of 1 over s minus z plus 1 over s minus 1 minus the complex conjugate of z. So what about this function? His fundamental observation is that if real part of z lies between 0 and 1, then this particular difference f of s comma z minus 1 over square root of 5 f of s1 comma z, which we will henceforth call Stechkin, the Stechkin difference of the function f, this will turn out to be greater than or equal to 0, but every assumption that we have made here plays a role. Okay, so your sigma does have to lie strictly between 1 and phi. If that happens, and if real part of z lies between 0 and 1, we end up getting non-negativity of this Stechkin difference. And this is going to help us because if you recall when we had the Hadamard factorization formula, we had terms of the form real part of 1 over s minus rho, where rho was coming from non-trivial zeros of the zeta function. Now we consider a polynomial, some polynomial which takes only non-negative values. At the moment it is not important what these a sub k's are, we will optimize them later. So let us take a polynomial of any given degree which is greater than or which takes non-negative values. Define g of z to be the real part of minus zeta prime over zeta, which is the quantity that we had considered before as well. But now we actually take the Stechkin difference of this function g of z. So we take g of sigma plus I k t minus 1 over square root of 5 times g of sigma 1 plus I k t, combine it with the polynomial that we have taken and call this function s of t. And because of the Dirichlet series expansions of these functions, and the fact that p of theta is non-negative, we end up getting that this function, this Stechkin difference of the polynomial applied to g is non-negative. So 0 is less than or equal to s of t. And now we can also study s of t using the formula that is coming from the Hadamard factorization. So into s of t you plug in the Hadamard factorization, and I know it's getting technical, but the main thing to focus on is this particular sum. When we put this into the Stechkin differencing, we observe because of Stechkin's observation, again we will get that each term in the Stechkin difference of this sum is non-negative. This comes from the previous observation here, this thing here. So once again we are allowed to isolate a 0 of zeta of s in the above using Stechkin's observation, and then we do some technical calculations. So now here we will need to obtain bounds for the Stechkin differences corresponding to the logarithmic derivative of the gamma function, and this can be done. It is some technical work, but Stechkin did it. But the core of the argument is how the observation of Stechkin applies to this sum coming from the zeros of the zeta function. So using this, one gets a nice inequality which is similar to the inequality that we had. It is a little more elaborate, but the good thing is all these constants that that show up in this inequality are known. We have precise values for them. And again we make this a similar choice for sigma as we had done before, and then evaluate what would be the optimal choice of polynomial to give you the best possible, sharpest possible zero-free region. So the optimal polynomial turns out to be this particular trigonometric polynomial of degree 4. and it yields the following bound for beta. So, beta is less than 1 minus 1 over 9.65 times log of absolute of T0, provided absolute T0 is large, is sufficiently large, which is again precisely stated if it is greater than or equal to 12. Okay, so this is basically Stechkin's argument applied to the Riemann-Zeta function. So, if you want to apply Stechkin differencing to symmetric power L functions, so what do? So, you consider, given your f of z, so let alpha 1 of p and alpha 2 of p denote the local factors of our corresponding to the eigenvalue at the prime p, and using these we can construct the Euler product representation of our symmetric power L functions, which are given by this which is given by this formula in the region real part of s greater than 1. So, what Newton and Thorne showed was that this completed L function, because of its connection with automorphic L functions, because of its automorphy, this completed L function is now an entire function on C. So, now what are these factors here? This is just the symmetric power L function, and these are the gamma factors corresponding to this L. So, this is a product of a bunch of gamma functions. So, it satisfies the following functional equation, and using the Hadamard factorization of this completed L function lambda, we can derive, in the spirit of what we had for minus zeta prime by zeta, we can derive real part of minus L prime by L for the symmetric power L function, and this has a very precise formulation provided your capital N is square free. So, this is m over 2 times log n plus the real part of the logarithmic derivative of the gamma factors for this L function minus real part of the sums of these reciprocals of 1 over s minus rho, where rho is again coming from all the non-trivial zeros of the symmetric power L function. So, see, in spirit this is very, very similar to the zeta function, but now you have to do more elaborate calculations for to obtain bounds for these terms and so on. Okay. So, how will the positivity argument work here? So, the logarithmic derivative, which so far we had expressed the symmetric power L function as an Euler product, and we can exploit that to write out a Dirichlet series representation for the logarithmic derivative of these L functions, and where these coefficients lambda of n and lambda corresponding to sim to the m of f will show up, and this equality, this Dirichlet series representation holds for real part of s greater than 1. So, what kind of a polynomial would we consider? Now, what we do is we consider the following polynomial p sub n, okay, which will keep changing with n. So, these constants a and b they are fixed constants which we will optimize and obtain later, but this is the polynomial that you take. Lambda 8 times a plus lambda sub f of n times cosine theta whole square times b plus lambda sub f of n times cosine theta whole square, and this is non-negative. And now the key work that happens here is, again we put this into a Stechkin differencing mode. So, we have 0 is less than or equal to this particular expression that comes from the Stechkin differencing, but because of the behavior of lambda sub f of n, it turns out that this particular sum can be written as this elaborate sum coming from various types of Rankin-Selberg L functions corresponding to f. Okay, so, these are the Stechkin differences that show up. Okay, this is the original Stechkin difference for the zeta function, then you have Stechkin difference for your LSF, and then for m equal to 2, 3 and 4, you have the double, triple and quadruple Rankin-Selberg L functions, and you have to put your you have to derive these Stechkin differences. So this, all the work, the technical calculations start at this stage. So first we determine the relationship between the symmetric power L functions and the Rankine-Selberg L functions by comparing their Euler factors. Then we can use the Hadamard factorization for the symmetric power L functions to derive the Hadamard factorization for these Rankine-Selberg L functions, and then we bound each of these Stechkin differencing. So this takes a while. This is the most elaborate part of the argument, but when we put it all together, we get an inequality of the form that Stechkin had obtained for the classical zeta function, and we know A, B and C are explicit quantities coming from the choice of our polynomial, and when you optimize to suit this method, the optimal choice here turns out to be this. Okay, and it yields this zero-free region. So it yields that if your beta is the real part of a 0 of LSF, this is bounded above by 1 minus 1 over 16.71 log of absolute T0 with the restriction that absolute of T0 is greater than or equal to 1. Okay, and I will just make some concluding remarks. So explicit bounds for the partial sums of the von Mangold function and error terms in the prime number theorem using zero-free regions of zeta of S have been very well studied. Tons of methods are known to study this. A very, very classical set of classical papers in this direction is due to Rosser and Schoenfeld, written in 1962 and 1975. So if there are any graduate students here who are interested in this area, Rosser-Schoenfeld papers would be the literature to begin with. And the later paper, 1975 paper, uses Stechkin's technique to improve bounds that had been obtained in 1962. Later, of course, once you have something for the zeta function, you can also ask if it can be adapted to other types of L functions. So Macaulay adapted Stechkin's technique to derive explicit zero-free regions for Dirichlet L functions. And the state-of-the-art bound using Stechkin's technique right now for zeta of S is due to Habiba Kadiri, who derived this bound here. So she improved the constant from 9.65 to 5.60. And as I had mentioned before, Stechkin's technique has been adapted to modular L functions for the first time in our current ongoing work, but there is more to do. We can also ask about explicit zero-free regions for symmetric power L functions using the same technique, and that is work in progress, but I thought I'll present to you what happens for LSF. And I conclude by, I want to show this picture. Why did it go? Yeah. Okay, maybe just show this. Okay, so this is from another birthday conference at IMSE, I think in the year 2002. It was a 80th birthday conference for Professor M.V. Subbarao, and both Kalyan and Shridi are in this picture. Kalyan is wearing a nice Superman t-shirt, and many other audience members are also in this picture. So Adhikari, Ramki, Shauli, Purushottam, I'm not sure if they are in the hall right now. Shanta is there. Hidden between Suri and Adhikari, and Eknath is also here, and if there are others, perhaps you can. So happy birthday again.
Okay, thank you very much for this very interesting talk. And are there questions, comments? Yes, Shankar?
Assume no Ziegel zero or something.
Ziegel zeros for Riemann zeta?
No.
Yeah.
The L functions you are considering,
No, we don't need to consider Ziegel zeros. for
Okay.
them. Yeah.
So I notice finally only the first 4 symmetric powers seem to play a role in sketching.
Finally.
So do you really need the automorphy of all of them, or do
No,
you?
only 4. We only need for M up to 4.
Okay, in which case would it also apply for mass forms, because you know everything for the
Yes.
first 4 symmetric powers of mass?
Actually, yeah, I think it
Yep.
should apply.
Okay.
Yeah, thank you.
Peter has proved the general zero-free region for GLN custom, the analog of Vinogrado. So yours is an improvement in terms of the constants or what?
In terms of the constants.
Okay, good.
What is so special about phi?
Phi?
The golden ratio you're taking 1 plus root phi by 2. Because
Okay.
that is your starting point, right? You have
Yeah.
your phi and sigma 1. So
Yeah.
what is so special about
Yeah,
phi?
it's to do with this Stechkin difference. Let me just go back to that slide. This particular form of Stechkin differencing, which involves 1 over square root of 5. So this non-negativity works only when sigma lies in this.
No,
Yeah,
it
so-
seems that you're starting with some constant, and
Yeah.
then you are constructing everything to work for that constant.
No, it was actually the other way around.
Okay.
If you look at Stechkin's paper, he mentions f of s comma z minus some kappa times f of s1 comma z and then optimizes
Okay.
further.
Okay. Thank you.
Hi, Karinika.
Hi.
Here.
Okay.
Nice talk.
Thank you.
So, do you expect analog of Vinogradov for this zero-free region?
Yes, you mean the error terms?
Yes.
Yeah, if we can derive zero-free regions for all the symmetric power L functions, then they could be
Then it will
be
give.
combined too. Possibly. I don't know yet.
So, okay, if there's no more question, thanks again.
Thank you.
Okay, still working on the names of the organizers.
So now there is a special lunch in tennis court, that is in the right side. Okay, after going from Ramanujan auditorium, this is in right side, take 2 times right side and tennis court is there. Next session we start at 2:30.